Okay, so now that we have 3 spheres set up, we can move on with a few more interesting things, because now we're ray tracing 3 spheres, but we don't really have a light source or shadows, which we kind of want to have. One thing we're going to do is we're going to add another sphere in the bottom. So I'm going to call this SB4, why not? And what the sphere is going to be is going to be used very easily for now as a floor. So it's going to be a very big sphere. Let's say 5 for the radius. And its center is going to be centered here. The AD is going to be 3. And basically it's going to be, let's say, -3. Sure. See what this looks like. Okay. As we're going to take the SB4. Also, there's a better way to do this. As you might imagine, I said 4, though it should be 3. But might as well do it like this for now. Okay. And so if we hit this one, we're going to consider this the floor. So that's going to be return. Color dot. Good question. Let's say magenta, because why not? So now, there's an error here. Unknown reasons. Oh. Float it was. So if we run this now, we should have a floor. Hopefully it's not going through the other spheres. Uh-oh, it's not there. Let's say 2. That might be a better bet. I really thought that seems to me like something. Yeah. So 3 is too much, but 2 is not. So let's say 2.5. You can see how cool this looks, though. So we're doing this because we want to have a floor so we can cast shadows. Oh, I hate you. 2.8. Okay. Regardless, I'm going to make it larger as well. So one way to fix this would be to say this is a 7, because I do want it to cover all of the spheres like a floor. So it's going to be a very large sphere. I kind of played it a bit too safe. Yeah, something like that. And it's just going to be 3.5. So let's have half the radius be down. But we can't see it. Okay, well, I'll make sure that. Is it good enough? It is not good enough. I'll keep going till I find the thing that I want, because we do want it to be visible, so. Okay, let's keep it like this for now, despite the fact that it's probably not going to stay like this. Cool. Also just realized these spheres we've pushed to a depth. So that's why this looks a bit weird. So let's put this to 6 on the depth. So it actually was translated on the z-axis. That's a lot better, despite the fact that it's going through it. I'll say 5, and I'll make it, yeah, I'll leave it like this for now, and we'll figure it out when we move on. So the first thing we're going to do is we're going to define a point light. So I hate you. Anyway, so I'm going to go here, and I'm going to right click and new, and I'm going to call it point light. Now, this isn't really going to be a very important thing to have, because also I'm realizing I'm just... So we're only going to just describe our point light here. So all we need, believe it or not, is a position, and then we need a color. So what color is the light, basically? So we have val, pause, flow 3, and then we're gonna have val color, which is also flow 3 because that's nice. And that's literally it. We're not gonna do anything else with it. So let's create a point light. So let's say light 0. It's a point light, and it has a location at 0.0 here, 2.0, let's say on the y-axis, or let's say 3.0 on the y-axis, and then let's say how far? Let's say 6.0f. Sure. Okay. And then we're going to define the color, and I'm going to define it as, let's say, well, I'm going to give it a color here. That's going to be a white color. So this is going to be 1. And X, Y, and Z are going to be 1. And I'm going to multiply it by 100. Just to give it a bit of power. Because remember, this is not a color thing. It's also how much brightness we're carrying. So there is a meaning to the 100. Okay, so we have our point light. The next thing is to actually change this a little bit. So this trace ray thing runs this and checks, well, intersects with all of the objects that we have, all of the prims that we have, and depending on what we hit, if we hit something, it behaves accordingly. Well, this time we're not going to be just giving a color. So basically this is going to change a little bit. What that means is we're going to actually do something. We already talked about it. We're going to actually use direct illumination. So in this case, we're going to say, obviously we have colors here. I will actually change these colors. We'll keep them for now, but just as an example, I'm going to put this here, and I'm going to create a new function that's going to be direct illumination. So that's going to be giving us the final color that we're going to be returning. And that function is going to be it's going to have our ray, and it's going to have our color for this specific prim. So it's albedo color. So let's say that this one is completely red. And let's say that this one is green. This one is blue. And this, because it's the floor, let's say that it's a combination of these. Okay. So obviously this function doesn't exist, so we need to create the function. So we're going to go here. And sure. Now let's put it above our trace ray. So fun, direct illumination. And yes, the first thing is a ray. And the second thing again is, well, what should we call it? Let's call it surface color. Sure. That's not horrible. And it's going to be float3. And it will return an int, right? So we'll return our packed, basically, colors into one single int. So we're going to use our function that we created here, which is this one, in the end. So a few things. The direct illumination here, generally in ray tracing, we can sample a light. So a light is not going to be a very specific spot in the world, right? Because the point light that we just created is literally a very specific spot in the world. It's not a surface. It's not a lamp, or it's not a light bulb, you know, that has a surface, or a quad light or something like that, or a sphere light. So that means that we're not going to be sampling it. So that means that we're always going to hit the same spot, because the light is in only one spot in the world. So obviously this isn't a very good representation, but it is a very simple way to do it for now. So a few things. We want to see if we hit the light. That's what direct illumination is going to be doing. So to see that, well, imagine that we're casting a ray from our eye and we hit this magenta thing that is barely visible. And we want to know if that thing is reachable by the light source. So we hit it here. So we create a new ray, and we trace that ray from this point to the position of the light that we just defined. And by doing that, well, that is obviously we have the origin being here, then we have the direction, which comes from the obvious. We just create a vector from here to the light. And the actual, we will normalize it, and the actual T of the ray, if you remember, we have a T for the ray. So the T for the ray is going to be our very nice distance between this point, the intersection point, and the light. So we will start off by defining that. So we're going to have a val I, which is going to be our intersection point, just as before. So ray, intersection point, that's going to give us the intersection point. Cool. Then we need a normal to that intersection point. That is very important. So, okay, well, we already have that function. And that's really nice. One unfortunate thing is we don't know here what we hit, and you can see the problem because we don't know. You have to check if it's SP0, 1, 2, 3, or 4. So what we're going to be doing for this, just to fix this tiny issue, is we're going to create a new thing on the top. We're going to actually create a lot of things. So here, under everything, we're going to say val, and we're going to name something called prims, and it's going to be an array of. So it's going to create the type, basically, of the array on its own. It's obviously an array of spheres, but you know. Okay, there is no SP. Okay, so now we have an array that actually showcases that. I will change it eventually on the trace function, but for now we're going to keep it like this. Cool. So we have our spheres. Now we can go down, and here we can say, well, we have, well, it's 0, 1, 2, 3, and that's how they're placed in the array, and they have ID 0, 1, 2, 3. So n will be prims, because remember the normal we get from a function that is in the sphere class. So this function is to be called from the right sphere. So we're going to say ray, and we're going to prims, and the index for that is going to be ray.objectIDX, and we just do get normal, and we pass the ray, and that's it. And that's how we get our normal. Cool. The next part is to define the actual vector. So here we're going to say val L, is going to be equal to, what did I say? Point light or light? Light 0 dot position minus I, just as I said before. So, we go from the intersection point to the position of the light. Okay. So now we need to calculate the distance. And that's very nice because we do have a length function that we created. So all we have to do is take this vector L and use the length function that we created to actually get the distance. That's pretty much it. Now, because remember that we're talking about a ray, we want the direction to be normalized. So now we can say L dot normalize, and now our vector is normalized. So L now represents just the direction, and the actual magnitude is here in the distance variable, or not really a variable, or constant. So let's now, we're gonna actually do some weird things for the light normal. In general, we do some weird things because it is going to be a point light, and those suck. But first of all, we need imagine a light. If a light had a normal, it would point downwards. I mean, it can point both ways, but imagine a light that only shines downwards, like many lights do. So we're going to say here val light normal equals flow 3. So this is going to be just the direction of the light. So obviously this is going to be 0. This is going to be minus 1.0 f. So it's pointing downwards, and this is going to be 0. And obviously this is a nice normalized vector. Now, a few things. I am going to actually talk about these mathematics in a different video because somebody might want to skip them, but I still think they're very important. So I'm not going to make them part of this. I am going to explain them in another one along with the intersection of the sphere, because why not? It's easy to explain. So yeah, look for that if you want to know what is happening here. So we have two cosines that we care about. They don't really matter here as much, but if we had a proper sampling task, then yes. Because imagine that, well, this is a single point in the world, but if we had a quad that is a light, then we would have to figure out where we hit it. We're talking about direct illumination. Okay. Well, then this L is going to come obviously from the intersection point, but where is it going in the light? Like, is it the center of the light? Is it the position of the light? Is it some corner of that quad? So then it's a sampling task. So things change a little bit. But in our case, we can only hit a single point in the light, which is its position. So we're going to start with this one. And we're going to say light normal dot. And you probably already are figuring out what's going on here. So we're going to figure out a cosine of two normal vectors by using a dot product, which is really nice. And cosine I is L dot N. So we have two cosines. So I don't think I need to explain why that's true. The reason why it is true, very simply, very quickly, is the dot product is between two vectors. That is their magnitude, the product of their magnitude times the cosine of their angle. So quite obviously you figure out that, well, these are normal vectors, they're normalized, so that they have a magnitude of 1, so that's gone. So basically the cosine is indeed equal to the dot product. Cool. So now that we have them, we're gonna have a nice here check as to whether that light has been hit, basically. Again, gonna explain these a little bit better or explain them, I guess, on another video. Cool. So this, if we enter this, well, let's say what happens if we don't. If we don't, we just return black. So we are certain that we're not hitting the light. This is not very useful here, but I'll keep it because if we extend this to a quad or something like that, this is going to be useful. We talked about primary rays, and those are the rays that come from the camera. But what about rays that bounce off the floor, or not really bounce off the floor, I guess in our case, but rays that we use to check whether we get light? Those are called shadow rays. And there are reasons why they're called shadow rays, and basically they're the ones that create the shadows. If we don't hit the light, because for whatever reason there's something in the middle, so if we hit this, check if this point is being hit by the light, there might be a sphere that actually occludes this point. So if that happens, then this needs to be darkened or black because we need a shadow there. So this shadow ray has a very good advantage that we don't really need to check. We obviously need to trace it, but we don't need to check whether we hit the closest object. Basically, if we hit any object, then we know that we can't reach the light. The reason that works is because our T in our ray is not infinite. So this will go only from here to the light. So anything that we hit between these points is always going to be between this and the light. It's not going to be further than the light, for example. Cool. So I'm going to say here, set up shadow ray. I cannot type shadow ray. I'll not call it shadow ray in one word, just shadow ray. So we need a new, I'll just literally call it shadow ray. A new ray that is going to be defined, obviously starts from the origin point, which is I. But because we want to be a bit smarter, we're actually going to slightly move it from, because right now it's exactly where we hit, right? It's exactly on the sphere. But sometimes we want to actually be a bit further away, and that's for numerical reasons. So we're going to add something to this. We're going to say I plus, we're going to go towards the direction of the ray, which is L. I don't know why I typed D. And we're going to go towards that direction for epsilon. And that's the machine epsilon, which we have not defined. But we're going to define. We're actually going to be defining quite a few things here. So we're going to have epsilon. And we're going to say that that epsilon is, in our case, 0.001 F. It can be other numbers, but this is pretty good. Cool. Where was I? Okay, now we have the origin point. The direction is going to be just very, very, very simply L. Okay, now the last thing is we have to say that the T is not infinite because remember, it will be initialized to infinite. It is actually equal to distance, which is this. Okay. In fact, we can be a bit more interesting about the distance and say distance is going to be that minus 2.0 F times epsilon. Just so we don't keep the distance to exactly where the light is. Cool. So then here, I'm going to say, well, we're going to do the occlusion check. So we're going to say init distance to store the initial shadow ray distance, and there are reasons for that. And now I can actually check whether I'm hitting something. So I do have to intersect everything again. So I'll take all of these, and obviously now I'm going to have the shadow ray. Cool. And for every single one of these, let's be smart and let's just do it now. So we're going to say for I in 0 until prims dot size. What? Sure, that's good enough. So we're going to check every single one of these, and we're going to do this for these as well. So let me comment these out just in case we need them. So basically this one is going to be prims I dot intersect right. Cool. And the same thing is going to happen here. So we're going to say prims I dot intersect shadow ray. Okay, so we check whether we hit each of these with the shadow ray that we just created. In this case, it is very important that, so if we hit something here, we're going to say if prims, sure. So if prims I, not prims I, so if shadow ray smaller, yeah, let's put both checks in here. So it's dot t has become smaller than the distance, so it can only become larger. So it has a smaller, and shadow ray dot object ID x is different than -1. So how we hit something, because remember it will be here initialized to -1. So then we just return color dot black because we hit something. However, if that does not happen and we reach this point here, that means that we have actually made it. So we didn't hit the light, or we are hitting the light. In this case, we'll have to calculate up our BRDF, which I'm also going to explain in another video. So I'm going to say BRDF calculation. Now here, this isn't that important, but otherwise it would be. If we had a different type of light, that is. So we have a BRDF that's going to start with flow 3. And obviously this is going to start as basically the inverted pi. And I'm going to call it inphi, and I'm going to define that because that's nice to do. And we do the same with pi, so we will define what that actually is. In this case, it is a very large number that I'm wondering now, does pi exist here? Like a math or something? Math dot pi. Oh, cool. That works. And I'm going to say this is 1 over pi, which isn't exactly what we would normally do, but for now, that is going to be enough. Cool. And now I'm going to go back to where I was, and this has been defined. This is double. I'm going to turn this actually here to float. Okay, because we don't want a double. We don't really need that much precision. Not in our case, it's a phone. So we have our BRDF start point. That's why we called it a var, because it is going to be changed. The next step is basically to multiply this BRDF. So we're going to say times equals with the surface color. So we have a surface color. That's what I called it, right? Yep. And we multiply it, so the color of whatever we hit initially. Then we'll use something called the solid angle, which doesn't matter as much here, I think. But we're going to add it anyway, in case we change the type of light that we have. So the color, so the final basically color, is going to be BRDF times the color of the light, because remember we need to keep that in mind. So we have to say light, we only have one light, dot color, cool, times something called the solid angle, times the cosine I. So we need to define that solid angle quite obviously. So this val solid angle is gonna be so this is not 100% correct, but it works for this case. Cosine 0 over distance times distance. So this is basically how we add the fall off of the light, because remember that it is like if it's further away we shouldn't have as much light. So for that reason we need to multiply it by something, and this is what you see, it's the inverse square that you will see for the fall off. Cool. And this is going to work well enough. Here we're going to say return, obviously the color. We can't just return the color because we said we were returning the int. So we're going to use our RGB32F to RGB8 and just have the color here. And that's literally it. So now, with a bit of luck, this may or may not work. Let's see what happens. Ooh, cool. So you can see that indeed these are now being lit by something, and you can see the fall off here based on the angle to the light, and that's what the solid angle is supposed to do, right? And the distance as well. Of course, I kind of put it too far off. Let's put the light further towards us and not that much in the back. So let's say 2 here. Or 3. And let's fix the stupid floor and make it like 20 or something. Like make it really large. And see what happens. And you can see the order of the spheres as well as intended. Cool. One problem is that this looks off. Let me fix that. Let's put it, you know what, let's put it to 50. But like, let's put it really low so that it is actually like a floor. This is not gonna work, by the way, quite obviously. I don't know why I run it again. Where have you gone? What are the chances that we're inside the sphere? No, that wouldn't work, because we would hit the backside of it. Okay, that's better. Not really, but it's just... so if I say 10... for whatever reason, this thing disappears. Yeah, I guess things are really... yeah. It goes too low. Can't really... I hate that I can't see down because of we haven't added the input to the camera yet. We'll do that. Yeah, so anyway, this is a bit of a weird effect that happens. We're going to have to fix that. But you can see that shadows do work. Yeah, I mean, we get this. So you can see the shadows and how they work. And how this is just missing here and it's back here. So yeah, that's working as intended. And yeah, that's pretty good. So we'll have to do a few other things to make it work a little bit better. But yeah, you can see that now we have shadows and we have a light. So things are actually been lit. And things will be changed if I change the light, because right now it's just a white light. So it doesn't really change anything. when it's multiplied, it does change how much these are bright, but the color of the light is just 1. If I changed it, however, so I said 0.0f here and 0.0f, then you will see that the color of these is going to change as well. So everything will become a bit more red, or a lot more red. We don't really want that. Okay. Cool. So we're going to leave it like this. Usually you will not do this. You'll have a light that's bright in all colors in some way. Okay. And that's pretty much it. And the next one, we're actually going to add, I guess we're going to add an HDRI image. So we're going to have a sky dome. And finally, we're going to have a nice sphere that we're going to have a mirror sphere. Right now, we can't really reflect anything. We might start with a mirror, and then, because that's super easy, and you'll see how that works. And so we're going to make perhaps the middle one mirror, and then see the other two reflect on it, well, the floor as well. And that's it. So see you on the next one.